In this video, we'll look at op-amp limitations. In the last video, we considered this circuit, which is a difference amplifier. And if we looked at the transfer function of this circuit, the output was an amplification of the difference of the input voltages. So we can summarize that equation with this equation here, and the output voltage is just the difference in the input times by some gain term. In reality, we don't get that. The output voltage is what we expect, this amplification. However, we've also got what's called a common mode voltage gain, which is this term here. So to explain how that works, if we take an input voltage of 3.02 volts and another input voltage of 2.98 volts, then the difference is 0.04, and this is what we'd expect to amplify an output. However, the average voltage, or the common mode voltage, in this case is 3 volts. It's the average input, and this 3 volts is also amplified to a certain extent and added to the output. So our output isn't just the difference amplified, it's also the average voltage of the two inputs amplified. When you buy an op-amp, one of the characteristics is what's called the common mode rejection ratio, CMRR, and that is the ratio of the difference gain compared to the common mode gain. So in an ideal op-amp, this term is large and this term is 0, and therefore CMRR for a perfect amplifier is infinity. In practice, they're more something like 80 to 100. Okay, so you do get mostly amplification with the difference in the voltage, but you do get some amplification of the common mode. And the higher this value, the better the op-amp, and the less of an issue this is. If we look at some of other limitations of op-amps, we'll firstly consider what we class as an ideal op-amp. So we've assumed it doesn't sink any current. We've always said the current goes through the feedback loop, so it doesn't sink current, and it has an infinite input impedance. We've just put a voltage input into the op-amp. We haven't been concerned about what that voltage level is. So we assume it accepts any voltage, and we assume the resistance of the output is 0. So again, we haven't really mentioned that, but we're assuming an output resistance of 0. Unlimited current source. So we're just saying the output is a certain voltage. We're assuming that we'll be able to supply any current we want. Infinite voltage gain. So potentially we can have as high a gain as we want. The phase of the output, we haven't mentioned that, but we're assuming the phase, so the time delay in any of the signals, or there isn't any time delay, the phase is unaffected. We've just mentioned the common mode rejection ratio, that is our CMRR, and we're saying when the input voltage is exactly the same, the output voltage is 0. But as you can see from this equation, if this was 3 volts and this was 3 volts, then this term would be 0, but this term wouldn't be, so V out wouldn't be 0 in this case. So we know that isn't true. Characteristics are independent of temperature, so we haven't mentioned temperature at all, we're just assuming that. And the output can change instantly. So again, we haven't really worried about that, we just assumed it. So that's what we assume for an op-amp. So let's see in practice how well them assumptions match up. The op-amp does actually sink current. So some of that current does go into an op-amp. It's known as the input bias current. It is very small. So it's nanoamps for a bipolar and picoamps for a field effect transistor type of op-amp. So there is a small amount of current, and that ultimately limits the size of the resistor you can use in your feedback. So as I said prior to this, if you have too large a resistance in your feedback loop, then it will affect the transfer function. So as long as you keep your resistances to a few tens of kilo ohms or thereabouts, then this shouldn't be a problem. So this one is okay. A finite input impedance. So you have got a very high input impedance, about 1 mega ohm for bipolar, and another factor of 10 to the 6 up on field effect transistor type of op amps. So again, similar to the sinking of that, if you have suitable resistance values in your feedback circuit, then this finite input resistance isn't going to be a problem. The inputs must remain within a specified voltage range. This is known as the common mode voltage range. So if you imagine it in practice, if you put a very high voltage on an op amp, so if you put kilovolts for an op amp, you are going to blow it up. So there must be a limit to how much voltage you can put into these things. And typically the voltage is a little bit less than the supply voltage of the op amp. So if you're supplying that op amp with plus or minus 12 volts, then typically you want a few volts less than that is your input voltage. So you are limited by what input voltage you can put into these things. The output impedance is typically 40 ohms. So again, it's quite a low output impedance. So that doesn't really affect our circuits. The op amp load, or the op amp can source current of typically 20 milliamps. So this is fairly important because this then limits potentially what the output voltage can be. So if I just escape that for a second and go into paint. So if you imagine an op amp and the output voltage is here, and it wants to, the output voltage should be 1 volt, but you have got a resistor here to ground, and this resistance is 1 ohm, then you're going to need a current going through there of V equals IR of 1 times 1. So I equals V over R. So 1 over 1 is 1 amp. So in order to maintain that balance, you're going to need 1 amp of current going through there. The op amp can only supply a limited amount of current, which I believe we said was around 20 milliamps. So we can only get 20 milliamps going through there. So V equals IR. So 20 milliamps. So 20 times 10 to the minus 3 times by 1 ohm is 20 millivolts. So although the output should be 1 volt, because it's got a limited supply of current coming on the output, then the output's only going to be 20 millivolts in this case. So it depends on your load, but you've got to be careful that you're not trying to source too much current on the output of these op amps, otherwise you won't be able to maintain the voltage required. So provided you have high impedances on the output side, this isn't a problem. If your impedances get too low on the output side, then the op amp's going to struggle to supply that much current. Finite voltage gain. So we set ideally it's an infinite voltage gain. So we can have as much gain as we want, determined by the resistor ratio. There isn't finite voltage gain on these, and it's frequency dependent. So the higher the frequency of your voltage signal, the less gain is possible from the op amp. And this is defined by what's known as the gain bandwidth of the op amp. And each op amp in its specification comes with a certain gain bandwidth value. So a 741 is somewhere around 1 megahertz. So this means if you want a gain of 1, if you've got an input voltage and you want a gain of 1 on that input voltage, you'll be able to achieve gains up to frequencies of 1 megahertz. If you want a gain of 1,000 on that input voltage, then 1,000 times by 1,000 hertz equals 1 megahertz. So the highest frequency you can go up to in your input voltage, in this case, is 1,000 hertz, 1 kilohertz. Anything beyond that, you will not be able to get 1,000 gain. So the gain you want multiplied by the frequency of your signal has to be less than the gained bandwidth of your op-amp, otherwise you will not be able to achieve the amplification you need. You can work around that problem. So for example, we've got an op-amp, we've got a 10 millivolt signal coming in, we want 1 volt coming out, so we need a gain of 100. So we're going to use a resistor ratio of 1 kilo ohm to 100 kilo ohms. That's our gain of 100. Our signal is actually at 20 kilohertz. So if we use this arrangement, we have got a gain of 100, a frequency of 20 kilohertz. So 100 times 20 kilohertz is 2 megahertz. So using this op-amp and this gain, we're not going to be able to achieve the output of 1 volt because the frequency is too high. The gain and the frequency combination is too high. So therefore, we will not be able to achieve the amplification. To work around that problem, what we can do is use 2 stages. So in this case, we've got an inverting amplifier arrangement with a gain of 10. So we've got a 20 kilohertz signal with a gain of 10. So the product of that is 200 kilohertz. So that will work. And then we've got another amplification stage with a gain of 10. So again, we've got a 20 kilohertz signal, a gain of 10. So the gain bandwidth of that is 200 kilohertz. So although we can achieve a gain of 100 in one stage, so that is no good, we can achieve 2 gains of 10. And we're within the gain bandwidth of the op-amp, and we've achieved our 100 gain in total. So again, it's something to be aware of. You probably won't be using frequencies that high in this module, so this shouldn't be a problem. But when you go to more specialized applications where it's high frequency and you might need high gains, you're going to have to consider the gain bandwidth of your op-amps when you're designing your circuits. The 741 is a fairly sort of basic op-amp, so that's got a fairly low gain bandwidth of a few megahertz. You can get more specialized, more expensive op-amps with greater bandwidths, and therefore you can get sort of high frequency, higher gains with these. The phase shift, so that is how much the output has been delayed. So if this is our input, our output might be delayed slightly, so there might be a phase shift associated with the output. So normally we're not too worried about the phase if we've got an input signal, unless we're actually wanting to measure a phase shift in the signal, then we won't be too worried about phase. So we kind of just live with any phase delay in our signal. So it's not usually a problem unless, as I said, you're actually wanting to measure a phase shift. The problem does come, however, when the phase shift approaches 180 degrees. And the trouble with that is what you have in your op-amp is negative feedback. So you've got an op-amp arrangement here with some negative feedback going into it, for example. So we've got feedback going in here. If this is in phase with the input, then the negative feedback gets taken away from your input signal minus this feedback signal is then calculated here. If you have a 180 degree phase shift on your output signal, then that is essentially multiplying it by -1. So you have your output that is then negated, but is going as negative feedback. So essentially what you have is then positive feedback. So if you get too much phase shift, you get a phase shift of 180 degrees, your negative feedback then becomes positive feedback, and then your circuit becomes unstable. Okay, so phase shift usually isn't a problem. However, if you're getting 180-degree phase shift, and that's when you're trying to go at higher frequencies at high gain, you start getting these phase shift problems, and it can lead to instability in your circuit. So not something to worry about in this module. We won't be pushing our circuits that hard, but again, something to think about with more specialized circuits. The common mode voltage gain is never zero, so we've looked at that. And again, if I go to paint, we've set our common mode voltage. Our common mode rejection ratio should be as high as possible. That's a finite value of maybe 80 to 100. So what that means is even if our input, so even if our input voltages are the same, V1 equals V2, then our V out, which equals GD times dV, all that should equal 0 in that scenario. Because we have this common mode voltage gain, we get an extra term there, so we do get an output on this. Now if you think about to the op-amp, when we first looked back, we said we have arrangement of 8 pins. So this was our negative input, our positive input, our output. This was our plus voltage supply, and this was our negative voltage supply. I said there was 2 extra terminals here, and these were called the offset terminals. So that was an offset, and that was an offset. And the point of the offset terminals is what you can do is you put some kind of resistor arrangement in there. So I'll just put a variable resistor in for now. But you put some kind of variable resistor arrangement in there, and what that does is you can fine tune the op-amp to make this term go to 0. So you do have the option of adjusting the op-amp so you can get this output voltage to be equal to 0 when the input voltages are the same. So there is a way of getting rid of that. However, the only problem with that is this offset is temperature dependent. So this only works if you're in a very stabilized temperature. If the temperature changes, then this offset's going to change, and therefore you're going to get this voltage appearing again. So it's a partial solution, but not an ideal one. So there are better ways of working around this common mode voltage, what we'll see in the next video. The final point is the rate of change of the output. So if we have an input, again I will use paint, if we have an input voltage coming in, and for example the input voltage is a square wave, so we have this coming in as our input to our op-amp. Then our output voltage, we might want to amplify that, so we expect our output voltage, if I do it as grey, to be something like that. So it just amplifies the input. So that's what we'd like it to be. In practice, what happens is it takes a finite amount of time for the output voltage to change. So it'll come in here, and then it'll take a little bit of time to actually ramp up to that voltage. It'll go along, and then it'll take a little bit of time to ramp back down. So this is how fast the output can change with time. So in this scenario, you get a little bit of an error, but it's not too significant. If you take this to a bit more of an extreme, and we say our input voltage is changing like that, then because it's changing so quick, our output, because there's a finite time it takes to change, can't keep up with that. And therefore, it's actually starting to distort the waveform we want. Okay, so it hasn't got time to reach the level it's supposed to before it has to change again. So this is the slew rate of the op amp, and this has to be fast enough for the signals you want to measure. So again, that is something to be careful of. In terms of the signals we're measuring, these are again relatively low frequency, so the op amp will be operating fast enough to actually be able to change relatively quickly, so you won't notice any difference. But for higher performance applications, then this can become a problem, this slew rate on the op amp. So that's the limitations of op amp. So in some cases we don't have to worry about it. In other cases it's something that we kind of need to consider in our designs. So if you consider the limitation and then you design your circuit appropriate to try and minimize that effect. So what we'll do in the next video is looking at a way to design to get around one of these effects.